In software development, building a functional object is only half the battle. The other half is ensuring that the object remains secure and its data stays valid. Encapsulation is the fundamental concept used to achieve this goal. It's the practice of bundling data and the methods that operate on that data into a single object while simultaneously restricting direct access to its inner workings. Think of it as a protective shield around your code. Now, why does this matter? In professional environments such as banking systems, healthcare records, or payment gateways, allowing anyone to change data directly isn't just a technical bug, it is a major security risk. If a user could manually change their bank balance to $1 million without going through a proper process, the whole system would collapse. Encapsulation ensures that data can only be changed through specific validated channels, acting as your first line of defense against accidental or malicious data corruption. To really understand this, let's look at a real-world analogy, a vending machine. When you walk up to a vending machine, you are presented with a public interface. This includes the buttons you press to select an item, the slot where you insert your money, and the tray where your snack is dispensed. You can interact with all of these parts freely. However, the internal mechanics are strictly encapsulated. You cannot reach inside the machine to grab a bag of chips for free, and you cannot manually alter the prices stored in its internal computer. The machine's internal state, its inventory and its cash reserves is entirely hidden and protected. You can only change the state of the machine, like getting a snack, by following the approved rules. You have to insert the correct amount of money, then select a valid item, and only then do you get your snack. This strict separation between what you can see on the outside and what is happening on the inside is exactly how we want our code to behave to keep the system secure. Now you might be wondering, how do we actually tell our code which parts are public and which are hidden? Python manages this using a very simple naming convention that we'll look at next.
Continuing with how we build that protective shield, Python manages these levels of access using a simple but effective naming convention. Unlike some other languages that force you to use strict keywords, Python uses underscores to signal to other developers exactly how a piece of data should be treated. First, let's talk about public access. If a variable is named simply like self.name, it is completely public. As you can guess, this means anyone from outside the class can read it or change it at any time. Second, we have protected access. This is signaled by a single underscore such as self._salary. Think of this as a gentleman's agreement among programmers. It clearly tells others, please don't touch this from outside the class. It's meant for internal use only. However, Python doesn't technically stop you from accessing it if you really try. Third, and most importantly for our security, is private access. This is signaled by a double underscore like self._balance. When Python sees those two underscores, it truly locks it down. How does it do that? Python performs a process called name mangling. It takes your simple variable and internally renames it to something like underscore class name _balance. Because the name has been completely changed behind the scenes, it becomes extremely difficult to access from outside. This is how we truly hide sensitive data. To see this in action, let's look down here at our bank vault. In the center, we have this protected purple box representing our private data. Inside, we are storing sensitive items like the balance, transaction history, and PIN. These are totally blocked from direct access. What happens if someone tries to bypass the rules? On the left side, we see an attempt to directly modify the data saying account.balance equals -99999. Because this data is private, Python immediately blocks this action and throws an attribute error. You simply cannot reach into the object and overwrite its core data. So how do we interact with it? On the right side, you see the approved ways. We use methods like deposit and withdraw. Notice the flow here. The incoming data is strictly validated first, and only if it passes is the balance updated. If we just want to let people see the hidden data safely without changing it, we use a tool called @property. Down here you can see @property balance, which provides a clean, read-only view into the vault, while strictly preventing anyone from altering it directly. This perfectly illustrates our golden rule. All changes must go through validated methods, never directly to the source. This concept isn't just theoretical. It becomes an absolute legal necessity when dealing with real-world financial applications.
In the real world, especially in the Indian fintech sector with companies like Razorpay, Paytm, and PhonePe, encapsulation isn't just a best practice, it is a legal necessity. According to RBI regulations, financial data must be handled with strict integrity. If a developer wrote code like this, modifying the balance directly to negative 99999, it would allow a user to give themselves infinite money or create a negative balance without any checks. This is why a secure class must act like a store hub, storing the balance as a private variable. By forcing every transaction through specific methods, the system can ensure that every single change is logged, validated, and secure. This level of control is the only way to pass a security audit. Let's look at how this is implemented in Python code. We define a bank account class. In the initialization method, which sets up our object, we have three variables. The owner is public, but the balance and transaction history start with double underscores, making them strictly private. To allow the user to check their balance safely, we use the property decorator. This gives us a read-only window. If we tried to write to the balance directly, Python would stop us because there is no setter defined. Next, we have our gatekeepers, the deposit and withdraw methods. In the deposit method, we check if the amount is greater than 0 before touching the private balance. The withdraw method does the same, checking if the amount is positive and if there are sufficient funds. In the testing section, we see that depositing 5,000 works because it follows the rules. But withdrawing 50,000 is blocked by our logic because the balance is insufficient. Most importantly, if you try to print the private balance directly, Python raises an attribute error. The data is effectively hidden and protected. To ensure you have mastered these concepts, let's review 3 quick questions. First, why is direct access dangerous? Imagine executing this line of code. Without encapsulation, it executes immediately. With encapsulation, it would crash the program instead of letting someone hack their balance. Second, 1 underscore versus 2. Use 1 underscore for internal variables that shouldn't be touched. Use 2 underscores for critical data that must be hidden via name mangling. Third, what does the property decorator do? It makes a method act like a variable. So instead of a getter, you use clean syntax like .balance, providing safe read-only access. Now it is your turn to build a secure system. You are tasked with creating an employee salary class for an HR system. You need to create a method to set the salary that checks if it falls within a valid range of 15,000 to 5 lakh rupees. You'll also include methods for net salary and tax deduction, and a property for reading the salary. By mastering encapsulation, you have moved beyond simple scripts to building professional-grade software. You now understand how to protect data integrity and build secure, reliable objects for real-world applications.